a little bit. Okay, we're live. Okay, I don't know from screens. I guess that we'll just assume that they can see your screen, Caitlin. All right, so in lesson 3. So part A, the question asked, it talks about Engelmann syndrome, which is displayed in genomic information. In the case of Engelmann syndrome, the infant silences the paternally inherited alleles. Suppose little a is Engelmann syndrome allele, while capital A is the non-disease allele. The following cross is done. What are the genotypes and phenotypes of the progeny? So the way that we figured this out is we kind of just did a Punnett square and worked backwards. The genotype of the parents is heterozygous for both of them, and the progeny would have a 1:2:1 ratio between homozygous dominant, heterozygous, and homozygous recessive. So the phenotypes, you would have 3 normal and 1 with Engelmann syndrome. Part B, this question concerns the situation in Part A. The following cross is done. What are the genotypes and phenotypes of the progeny? So we end up having a 1:1 ratio of heterozygous and homozygous recessive. We have 1:1 ratio of normal and Engelmann. For Part C, suppose a woman has triplo X syndrome where she has 3 X chromosomes. However, the XX have been deleted from 2 of the X chromosomes in each of her cells. How many Barr bodies are found in each of this woman's cells? So when she has 3 X chromosomes, she's going to have 3 X inactivation centers. But when 2 of them are not there, that means that let's see. Deleted. I'm not even sure if I did this right. Let's see. Deleted from 2 X chromosomes in each of the cells. I think that we end up with actually 2 Barr bodies. I was originally thinking 1, but what do you guys think? Wait, no. I'm really confused here. Wait a second.
So,
no, I think it would still be 1 Barr body.
Yeah, I agree.
Yeah. Because
2 of the centers are deleted from out of 3, and so there's 1 left that doesn't have the inactivation center.
Right. Okay. Yep. So you would have 1 Barr body. Okay. Part D, suppose you isolate a cell from a female cat with 2 X chromosomes. However, the T6 genes on each X chromosome are non-functional, while the X-ist genes on each chromosome are functional. How many Barr bodies are expected to be found in this cell? So X-ist is being produced and T6 is not able to bind with it. So in this case, we will have 2 Barr bodies or 2 inactivated chromosomes. Okay, so that's it for part 1.
Okay, and then we decided we're gonna just skip over 2, right?
Yeah.
Okay. So 3, let me scroll down to 3. A woman's father has OTD, an X-linked recessive disorder producing mental deterioration if not properly treated. The woman's mother is homozygous and is unaffected. So question A is, what is the genotype of the woman's father and what is the genotype of the woman's mother? So from those, the father, I got X. What did you call it when you did the little notation? Can I just say notation? X notation 1, and then a Y, and then the mother I did double X for the genotypes. And then for B, if the woman has children with a man who does not have OTD, what is the chance that their first child will be a son with OTD? So now you just have to cross the woman with a man who is, I guess, normal, doesn't have OTD. And so you're gonna have a half chance, obviously, of it being a male. And then within that chance, you're going to have a 25% chance that he'll be affected with OTD. And then C is identify the genotype of a male with whom the woman could produce a daughter with OTD. So the genotype that I came up with was X notation 1 and then Y. And then D is consider the cross described in part C. So, what you have to do is then look at that cross, and then it says what are the expected genotypes and phenotypes of the offspring. So from that cross, you get a quarter of the genotype is going to be a quarter X notation 1, X notation 1, and then a quarter X notation 1, X, and then a quarter X notation Y, and a quarter XY. And then from that, your phenotype is going to be one girl affected to one girl not affected, and then one boy affected to one boy not affected. And then that's it for 3.
Awesome. So we have a question for them?
Yes.
All right. Question 4. The presence of a beard in some species of goats is determined by an autosomal gene that is dominant in males and recessive in females. Suppose that a cross produces a 3-to-1 beard-no beard phenotype ratio among the male offspring. What are the genotypes and phenotypes of the parents? So in this case, we would have both of the parents being heterozygous. This would result in a 3-to-1 ratio, because with the female, although she is heterozygous for it, the female parent, she would still be non-bearded in this case. For part B, suppose that a cross produces a 1-to-3 beard-no beard phenotype ratio among the female offspring. What are the genotypes and phenotypes of the parents? So for the females, this would be the exact same as part A. This would also be heterozygous B, heterozygous for each of the parents. And this is because it affects the females differerly. The female would have to be homozygous dominant B in order to be bearded, which with our Punnett square, we only have one of those. Let's see. So for part C, suppose a cross between a male with a beard and a female without a beard produces a 1-to-1 beard-no beard phenotype ratio among the female offspring. What are the genotypes of the parents? So in order for us to have a female with a beard, we know that the mom's going to have at least one dominant B, and the male in this case is going to have to give 2 dominant alleles. So the male will be homozygous dominant B, and the female would be heterozygous B. Part D, suppose a male and a female which lack beards produce a 1-to-1 beard-no beard ratio among the male offspring. What are the genotypes of the parents? So the male will be homozygous recessive BB, and he will be unbearded. I guess both the parents are unbearded. And the female will be once again heterozygous, big B, little b. That's it for question 4.
All right. So for number 5, first part is we're looking at coat colors in cats. The genotype of the progeny are 1 heterozygous female, one homozygous recessive, and that's a female, one male that has the dominant allele, and one male that has the recessive allele. We found this out just by doing a Punnett square with the parents. The phenotypes are one tortoiseshell female, one orange female, one black male, and one orange male. And part B is asking about the likelihood of having a male tortoiseshell cat. And it's not very likely because it requires, because this is an X-linked trait, it requires 2 X chromosomes so that there can be one dominant allele and one recessive allele. It is possible to have a male tortoiseshell cat, and that is if he has 2 X chromosomes, which is a mutation. That's not normal. So the genotype of a male tortoiseshell cat would be heterozygous in the X chromosome. So X, capital B, X, lowercase b, and Y. And part C and D, it's referring to a fruit fly mutation in the wing. So for C, we just used Punnett squares to find the reciprocal. So for the first cross, it was a male with the dominant allele, and then a female, which was homozygous recessive. The cross for that produced males that both had the scalloped wings, which is a mutation, and then the females didn't have scalloped wings. When we did the reciprocal cross, it was a male with the recessive allele and a female that was homozygous dominant. The result in that was that none of the progeny had scalloped wings. And so for part D, we saw the mutation as autosomal. So we did Punnett squares again. We had homozygous recessive times homozygous dominant. And that produced progeny that were all heterozygous. Then the reciprocal cross was heterozygous dominant crossed with a heterozygous recessive, and it was the same result. The progeny were all heterozygous. So when a trait is autosomal, a reciprocal cross will not produce a change in the genotypes and phenotypes of the progeny. And that is all.